I've been doing some more work with this Syscomp SIG101 signature analyzer, and I'd like to share some of that with you. One of the things that I would like to start off with is to say that, as I admitted in the first video, I'm still learning how to use this, and I still don't consider myself an expert at it, but I have learned a few things that I'd like to share with you, including the fact that I misstated earlier the way you read the voltage on the software, but I'll show you that in a minute. First, let me explain what I'm doing here. What I've done is I have used two different resistors, a 1K and a 50 ohm resistor, to see what the output of the device would be in terms of the maximum voltage, maximum current, etc. Now, the device says that the output is 50 ohms, and I take them at their word. They certainly should know how to rate these things, but because this is a combination of a wave generator and an oscilloscope input, I am hoping that they haven't paralleled 250 ohms or anything like that. I haven't tried to measure the output impedance of this device, but based on what I see, it looks like it probably is close to 50 ohms, and so I'll take their word that that is the output under signature analysis conditions, not just using it as a signal generator. So let me swing up here, and pardon the motion. I know that makes some people a little uneasy, but what I'm doing is measuring signal using this Rigol oscilloscope, and right now it's across a 47 ohm resistor. So what I'm going to do is raise the amplitude, and you'll see that there is some saturation where the device can't supply any more current, and so the voltage levels off at that point. Of course, this is to be expected. You can't, every device has a limit on how much, and because this is powered off a 12 volt, single-ended 12 volt supply, I really don't expect more than about 6 or 8 volts, maybe 10 volts peak to peak out of this. So let's go take a look now at the software again. Okay, first thing, in my first video I said that this measures 1 volt, and because they indicated across what looked to me like 2 divisions, I thought that was 1 volt across 2 divisions, or a half a volt per division. Let me be clear, I was wrong. This is 1 volt per division. In other words, right now, let me raise the amplitudes very slightly. Let me do it that way. And I have the amplitude set so that this is swinging approximately 1 volt positive and approximately 1 volt negative. So this legend down here of 1 volt means per division. And now that's measured on the Rigol oscilloscope, which right now is reading 2.97 volts peak to peak. So this is only an approximate figure, but you see that it's a little over 1 volt, a little over 1 division there. Let me see if I can reduce it just a little bit. It's hard to, oh, I see, it only does steps. So there, it's 2.3 volts peak to peak. So this is actually the per division. let's now go to say 500 millivolts, and let's go to 10 milliamps in that position. Okay, over here are some presets, and I have been using small signal even in the diode position, but it also has a power position and a Zener position, and we'll talk about those in a second. Right now, what I want to show you is if you raise, now this is a 50 ohm resistor that we're working into. If you raise the amplitude, you will see that eventually you get to a point where there is saturation. Now, this is showing saturation. I don't actually see that on the oscilloscope right now, but I do know that when I get up near the top of the range, I'm watching the scope now, okay, right about there is from there to there, so between, I guess, 90 and 95% on the amplitude, the saturation starts to show up clearly on the oscilloscope. So just be aware of that. This, remember, is working into a resistor. That is not a diode junction or a breakdown or anything like that. That is simply the characteristics of the unit when it reaches the limits of its internal circuitry. Now, what I'm going to do is reduce this back a little bit, and I'm going to go to the power position, which says plus and minus 2 volts. And once again, I'm going to go up, and you see it begins to limit. And right about there is where it starts to show up on the scope. Now let's reduce this to 2 volts per division. And you see, once again, we're getting the saturation. So what I'm pointing out is this is the region that you should be reading, and you shouldn't drive the amplitude, depending on the impedance you're going into, very much higher than that. Let me now switch to a 1K resistor and repeat some of these same measurements. Okay, as soon as I switch to a 1K resistor instead of the 50 ohm resistor, you'll notice that the voltage went off scale. So let's increase this to, well, that was at 90%. Let's reduce the amplitude till we're back on scale here. I'll set it at 45%. What I'm trying to do is to get this to let's go to 2 volts. And 5 milliamps. Now let's raise the amplitude here. And now we're in the power position. Okay, we're going to have to go to 5 volts. These controls are a little bit opposite for me. Okay, there you see there is virtually no curving there, a little bit of curving there, and that is on the scope 0.88 volts peak to peak. Now what I'm going to do is move this offset a little bit, because you'll notice that as you move the offset, the base of the swing changes, but the total amplitude doesn't. And I'll talk about that a little later, because when you're working on an asymmetric circuit, like a TTL circuit, where it's 0 to 5 volts, and you shouldn't be using negative voltages on a TTL, in a TTL circuit, you might want to move this offset up so that you're only going from 0 to some higher value. Right now, that shows a peak to peak of 10 point, well, it's varying between 6.6 and 0.7 volts. So now let's reduce the amplitude a little bit here. Let's go to 75%. Okay, and now it's reading 8.2 volts peak to peak. Let's move the offset down so that it's back at 0. Like that. Okay, so what am I saying here? Well, what I'm saying is, one thing you want to be careful of is some components do not tolerate swings in both directions. TTL logic, for example, expects its inputs and outputs to vary between approximately 0 volts, that is, whatever's on the ground pin of the TTL chip, and about 5 volts, which is what's on the VCC pin of the same chip. So just be aware of this, and you may need to preset your offset as well as the total amplitude. Now let's switch from the power setting to the small signal setting without changing anything else. Okay, you see it goes to a very, very small signal. So you may want to experiment with different components here to see what you're looking at. This is a 1K resistor, and oh, I see what it did. What it did when I went to small signal is it just reduced the amplitude. If I were to raise the amplitude, I'd be right back where I was before. Okay, all right. So the presets start out with an amplitude. Well, let's now look at the Zener preset. Okay, now it's set the amplitude to 100, and the offset to 0. Let's see what. Okay, I don't understand exactly what happened there because it seemed to be offset quite a ways, but when I moved the offset around, it came back to symmetric. Once again, like I say, I don't understand everything about this device. And by the way, let's get, we'll reduce the amplitude here a little bit. If you want, and you saw this in the earlier video, you can swap the voltage and current. Now normally voltage is displayed on the x-axis and current on the y, but if you click on swap, that swaps. And notice now it says voltage on y-axis and x-axis is current. So let's go back to the normal one. So the last thing that I'm going to do and then wrap this up is actually put a Zener on this circuit. First thing I'm going to do is reduce the amplitude down to maybe 20% or to 20. And so let me change and put a Zener in, and then we'll kind of close this video out. Okay, now I have connected a 4734 Zener diode, which should Zener at and by the way, it's backwards. Just so you'll know, this is actually the forward conduction, and so we're going to increase the amplitude until we see where it Zeners, or where the Zener conduction begins. Right now I'm set at 2 volts per division, so this would be 2 volts, this would be 4 volts, 5 volts would be about halfway between these two. So let's increase our amplitude and see where the Zener action starts. Okay, it starts at, let's see, that's 2, 4, 6, about 7 volts. Let me make sure that I have the right Zener in there. Yeah, that's a 5.6 volt Zener. So let's see if we move the offset down to, it should be around just under 6 volts. Okay, I'm not sure that I really understand what's going on there, but come back to 0 offset. But what you're seeing is the forward conduction of the diode here, and notice this is starting to get a little unstable here because the diode is heating up. There's a fair amount of forward current when it's in this at this end of the cycle, and the oscilloscope shows almost, well, not quite a square wave, but it's pretty truncated. So let me reduce this down, and okay, about right there, it comes out of saturation on the scope on this side, but this side, of course, is still being cut off by the diode. So let's now try power. Okay, that's 6.5 volts instead of 5.6 volts on this screen. Let me see if the offset changes that at all. No, it's still at about the same point. Okay, let's go then to small signal with the same diode, and you see it reduces the amplitude down quite a bit. And no, the Zener point is the same. Okay, well, here is what my preliminary guess about this is. I understand that there are calibration, you can actually do calibration inside this thing. If I remember right, it's maybe in the hardware menu, maybe tools. Yeah, calibration is in tools. I have not calibrated this unit, so it could be that if I calibrated it, that I would get a more accurate reading on this Zener voltage. But remember, we're just looking for qualitative, not quantitative results here. At least I was. I'm mainly interested in looking at inputs and outputs of circuits and seeing if they are, if two outputs look approximately the same. And so for that purpose, the calibration is not really that important to me, so I haven't calibrated mine. Those of you that have ordered these units, if you haven't already gotten them, when you do, you may want to check into that if the actual values are important to you. I have found over the years not to depend on values measured from generators. In this case, this is a generator and also an oscilloscope, but rather to use a calibrated, reliable oscilloscope or other measurement instrument that, I mean, there's no way that something that costs $100 is going to be anywhere near as accurate as, say, a 6-digit professional multimeter or things of that sort. So the use of this unit, I will kind of summarize by saying, first, I was wrong about the voltage levels here. This is apparently per division. The second thing is, I showed you that there are 3 different kinds of presets, and that you may want to use the Zener preset for higher voltage circuits, but beware that if you drive a circuit, say a TTL circuit, to much over 5 volts, you may actually damage the IC. So be sure you set this up in that way. Second, some circuits are not very tolerant of reverse voltage. So be aware that you could have a problem if you don't set the offset properly so that the voltage swing is within the range that the circuit or device you're testing expects. In other words, to put it simply, don't overdrive the circuit. The last thing is, I wouldn't depend on the absolute values read on this instrument because I haven't calibrated it yet. But if you calibrate yours, you may find that the values that you read are much more accurate than what I am reading. I'm not interested in calibrating this one. I'm more interested in just the general shape of the curves. But I hope this has all been useful to those that may have watched my first video and either gone out and bought one of these or are considering buying one of these, so that you'll understand that nothing that I have said in any way changes my opinion that this is a nice signature analyzer for testing transistor and IC based circuits. However, you do need to be aware of some of its limitations and also of some of the dangers of overdriving. So I hope you've enjoyed this one. I don't intend to do any more on the this SIG101, but then I didn't really intend to do this one until I started doing some additional work. So I hope you'll look forward to some more videos, probably not on this subject. And as usual, I hope you have a nice day.